All right, let's talk about string theory. You've definitely heard of it, right? It's one of the most famous, most ambitious ideas in all of modern physics. It's pitched as the final answer, the key that unlocks the entire cosmos. But what if it's actually nothing? What if it's the biggest dead end in science? That's what we're digging into today, why this theory is at the very center of a massive scientific civil war.
And you can see why people are so passionate about it. I mean, its promise is absolutely breathtaking. The goal here is to create a theory of everything. Just think about that. A single, beautiful, elegant equation that describes every force, every particle, everything in the universe. It's trying to do the one thing that has stumped physics for a century. Unite Einstein's theory of gravity, which governs stars and galaxies, with the wild, weird rules of quantum mechanics that run the subatomic world. It's the holy grail.
So, you'd think every physicist on the planet would be on board, right? Well, not even close. In fact, some of the smartest people in the field have called it things like a dead end, pure speculation, and some even go so far as to call it pseudoscience. So how is that possible? How can one idea be both the greatest hope for physics and its biggest frustration? Let's break it down. Now, the doubt surrounding string theory doesn't just come from super complex math that only a handful of people understand. Sometimes it all starts with a very simple, very human question. The kind of thing you or I might wonder while just, watching a documentary on TV. Take this quote from a writer named Benjamin Winterhalter. He's describing watching a science special, and the host just matter-of-factly says that string theory proves our universe has exactly 11 dimensions. And for him, that was the breaking point. It just sounded so arrogant, so certain. Where was the humility? And it turns out that gut feeling he had, what he called his half-drunk skepticism, was actually spot on. It gets right to the heart of the problem. Yeah, that feeling of, wait, how can they possibly know that for sure? That leads us directly to the single biggest criticism of string theory. It's a phrase you'll hear over and over from critics like physicist Peter Woit, the idea that the theory is not even wrong. And to understand what that devastating phrase really means, you have to understand one of the absolute bedrock rules of how science is supposed to work. And that rule is called falsifiability. It sounds complicated, but it's actually a really simple and powerful idea. All it means is that for a theory to count as scientific, there has to be some kind of test or observation you could imagine doing that would prove it's false. If your theory is so flexible that it can explain absolutely any result you get, then it's not really predicting anything, is it? It's more like a philosophy or a belief system, not science. And this is the knockout punch from the critics. As Peter Woit puts it so bluntly, after decades and decades of work, string theory has not produced a single unique prediction that we could actually go out and test. It hasn't said, go look for X, and if you don't find it, the theory's wrong. Think about that. If a theory can't be proven wrong, how can we ever have any confidence that it's right? And if you look at the theory's history, you can see why critics feel this way. I mean, it didn't even start out as a theory of everything. Back in the 60s, it was an attempt to explain the strong nuclear force. That didn't work. So in the 70s, it was repurposed to be about gravity. Then in the 80s, suddenly there were 5 different versions of it. Then in the 90s, something called M theory came along to try and unite those 5. Critics look at this and see a theory that's constantly moving the goalpost to avoid being killed. Supporters, of course, would say this is just how science works, it's a tough problem, and the theory's evolving as we learn more. But the question is a fair one. Is this progress, or is it just survival?
Okay, so let's move away from the philosophical arguments and get down to brass tacks. Because it gets worse. When the theory does require certain things to be true, those things seem to fly directly in the face of what we actually see when we look at the universe.
This is a huge problem. Let's break this down. First, for the math to work, string theory needs something called supersymmetry, or SUSY for short. It predicts that every particle we know has a much heavier partner particle. We have built the Large Hadron Collider, the most powerful machine in history, and we have smashed particles together for years, and we found 0 evidence of these partner particles. Not a single one. Second, the theory demands there be at least 9 dimensions of space. We live in 3. We have looked for evidence of others, and again, nothing. And maybe most damning of all, early versions of the theory pretty much required that the expansion of the universe be slowing down. Well, in 1998, we discovered the exact opposite. The expansion is speeding up. That discovery won a Nobel Prize, so it's about as solid as science gets. So, just step back and look at the situation. You've got a theory that requires things we can't find, like extra dimensions and partner particles, and it contradicts one of the biggest discoveries we have found, the accelerating universe.
you can see why critics feel like the tools of actual science, of reason and evidence, are just chipping away at the very foundations of this idea instead of building it up. So the theory is in a really tight spot, right? It's making predictions that don't match reality. How does it get out of this corner? Well, string theorists came up with an answer. But this answer has become maybe the most debated, most controversial part of this whole story.
So the theory adapted. In fact, it kind of exploded. It evolved into a framework that doesn't just describe our universe. Instead, it describes a gigantic, sprawling landscape of possible universes. And in this landscape, there are countless different universes, and each one can have its own different physical laws. Our universe is just one of the lucky ones where the laws happen to shake out in a way that allows for stars, planets, and us. And when I say countless, I mean it. The number of possible universes in this landscape is estimated to be 10 to the power of 500. Just try to wrap your head around that. That is a 1 with 500 zeros after it. There are more possible string theory universes than there are atoms in the known universe. And for critics, this is where the theory completely goes off the rails. If your theory allows for 10 to the 500th power different outcomes, it has lost any power to predict anything. All you can ever say is, well, of course our universe looks the way it does. We just happen to be in this one. It's not a prediction. It's an explanation after the fact.
And this is exactly the charge Peter Woit levels against it. He says that this multiverse landscape isn't some grand prediction of the theory. No, it's an excuse. It's a built-in escape hatch for why the theory failed to predict the one and only universe we can actually observe. So where does that leave us? We've over 50 years of research, thousands of the brightest minds on the planet working on this, and the debate is more heated than ever. Let's just pull together the final case against string theory, the core indictment from the critics. So here it is laid out. Critics say it makes no testable predictions, so it fails the falsifiability test. It requires things like SUSY and extra dimensions that just don't seem to exist. In over half a century, it hasn't gotten a single thing right that we can confirm, and its big solution, the landscape, makes it basically impossible to ever prove wrong. And there's a real-world cost to this. For decades, string theory has dominated theoretical physics departments and academic funding, which critics argue has starved other, potentially more promising ideas of oxygen. In the end, this whole debate is about so much more than just vibrating strings and extra dimensions. It's what the physicist Avi Loeb points out here. It's a debate that forces us to ask some really tough questions about how science itself works. How do we know when to give up on a beautiful idea? And is the survival of a theory based only on logic and evidence, or is it also shaped by things like culture, reputation, and just plain inertia? What do you do when one of your most promising ideas just doesn't seem to match reality? That is the profound and uncomfortable question that string theory leaves us with.